to have all the roots be the same. Now, that might not work out. You know, what if the sides of the triangle, what if your triangle had been 2 root 3 and 3 root 5 and 4 root 7? Well, root 3 and root 5 and root 7, do any of those simplify? No, none of them simplify. So what would the perimeter have been? 2 root 3 plus 3 root 5 plus 4 root 7. This particular answer would have been non-simplifiable. You wouldn't have been able to do anything with this because the roots can't be simplified to become the same. So there's just nothing to be done in that case. Nothing to be done. Yeah, they wouldn't simplify in the traditional way. Okay? But we lucked out. We lucked out that these could both be simplified into root 2's, and therefore they were all root 2's, and so we added them together. So how about this one, the rectangle? How big is this side? We don't know.
No, we do. It's 5 square root 6.
Oh, there.
Yeah. Yeah.
Oh.
And how big is this side up here, Olivia?
Long over here. 4 roots.
Yeah, very good.
I felt smart right there.
That's okay. I've made far worse mistakes. Okay, so now when we add these together, when we do perimeter, we could be nice to ourselves and go ahead and put the like terms next to each other, right? So 4 root 24 plus 4 root 24, since those are already common, I can already add them together. And then plus the 5 root 6 plus the 5 root 6. So at the very least, we can add together 4 root 24s plus 4 root 24s. That gives you a total of how many root 24s? 8 root 24s. And then if you have 5 root 6s plus 5 more root 6s, how many root 6s do you have? 10 root 6s. Okay, but we would like to try to simplify the root 24 and the root 6 to see if they could be the same. So root 6 is not going to simplify because 6 is not divisible by a square number. But root 24 probably will simplify. What square number goes in root 24?
4 and 6.
4 and 6. So 4 times 6, which is root 4 times root 6, which is 2 root 6. Hey, that's great. We did end up with a root 6. So once again, it's 8 times whatever root 24 happens to be, which is 2 root 6, plus the other 10 root 6s. And so what do we do here with the 8, 2, and the root 6? Just the 8 and the 2 multiply. So now we have 16 root 6s plus 10 root 6s. I don't know what it is about roots that turn me southern. I just can't help it. That's what you said earlier? Yeah, I just can't help it.
I mean, I like some roots come
What?
All right, so 16 root 6s plus 10 root 6s is 26 root 6s.
And roots will definitely give you the roots.
And so that's it. You know, folks, what if I had done my simplification earlier? Instead of going over here with all that, what if I had just right here said, well, that's really 4 times 2 root 6. So that's really 8 root 6. So then I would have 8 root 6, 8 root 6, 5 root 6, and 5 root 6. Well, now they're all root 6s already on my diagram, and I would just say 8 and 8 is 16, plus 10 is 26 root 6. And then I could have just said the answer was 26 root 6. So I could have done all the work on the diagram had I wanted to. So long as you do your sketch work, you know, so simplify your roots somewhere. Show your work. You want to look at it?
I like writing it out.
I like writing it out too. I think it's helpful.
I know what I'm doing.
Yeah.
Like following steps.
Yep. It's always more helpful to show work. All right. Very nice. Well, that was it for section 9.4. Yeah. So adding and subtracting roots, the rule is you need the same root. And if it's not the same root, they just don't add. So I just like to give one example of that. What if I gave you the problem 3 root 2 plus 8 root 3? Does this add together?
No.
No. It just doesn't add. And you might say, oh, but I want it to add. But if this was 3x plus 8y, could you add those together? No. So it's no big deal. You come up against non-combinable, non-like terms all the time, right? You can't combine like terms if it's x and y. You can't combine like terms if it's root 2 and root 3. They're different terms. So that's okay if they don't add together, but you have to try by simplifying the root. And that's why simplifying the root is an important skill. right, well, moving right along. It says, section 9.5, what skill are we working on in section 9.5? Yeah, multiplication.
What do you call that? Distribution thing. I mean,
Foil.
foiling.
Yeah, we're going to work on FOIL. Now, I would like you to notice really closely about root 7 plus 1 and root 7 minus 1. What are those?
The difference of squares. But
Yeah, those are
very common.
Conjugates.
conjugates. Those are conjugates.
Yeah, that one.
So we already know, if you want to write it down again, that A minus B and A plus B, those are conjugates because it's the same numbers but different signs. And the answer is A squared minus B squared. So if we wanted to just get a quick preview of the real answer, it would be what?
7 squared.
Root 7 squared
Yeah. Plus.
minus
Yeah.
1 squared. So we already know that's the answer. What's root 7 squared? 7. And 1 squared is 1, and the answer is 6. Now, I just used the difference of squares rule, right? And wasn't that convenient to remember the difference of squares? Because I was able to use the formula. That's interesting that I was able to multiply two irrational numbers, root 7 plus 1 and root 7 minus 1. I was able to multiply them together and get a regular whole number. Now, it's all well and good to remember the difference of squares formula, but you also need to know how to just do FOIL. So that's what this next problem is just pure FOIL. So you'll want to remind yourself, FOIL, first, outer, inner, last. So what's root 3 times root 2? Remember, you are allowed to multiply roots. So root 3 times root 2 is
Root 6.
root 6. However, so first, outer, you're not allowed to multiply a whole number times a root. So you just write them down together. So root 3 times negative 2 is negative 2 root 3. The 2 is simply being multiplied by the root 3. They just sit next to each other through multiplication. Okay, inner, what's negative 5 times root 2? Just negative 5 root 2. I like to think of whole numbers and roots like oil and water. Oil and water, they don't mix, right? They separate out. So when you multiply a whole number times a root, they just keep their identity as a whole number times a root. And then last, negative 5 times negative 2?
Positive 10.
Yeah, positive 10. Okay, so we have this situation here. And are any of them like terms?
Nope.
No, that's a root 6, that's a root 3, that's a root 2, and that's a no root. So there are no like terms at all, and we're just done. It's incredibly dissatisfying, isn't it?
Yeah.
Yeah.
But it was fun to FOIL.
Yeah, it was fun to FOIL, but that's the answer. Terrible. Now, of course, you can type that into your calculator and get a decimal, but this is the exact answer. This is exact. That's exactly what the answer is. It's just not a very good answer. It just occurred to me that'd be a pretty good insult. You're like a FOIL problem that doesn't simplify, or something like that. I don't know, just a thought. Okay. Continuing on, we have.
I don't know, I found that so funny.
I know, me too. I thought it was funny.
I love insults that like take a lot of.
There's no better insult than the insult that the other person doesn't even understand they're
Right.
insulted. Yeah, that's the best. Okay, so how about 71? Is that a conjugate?
Yes. No, because of the 2.
Yeah, there is the plus and the minus, and they're both root A, but the 7 and 2 are different. So to be a conjugate, it has to be the exact same numbers. More importantly, the whole point of a conjugate is that the middle terms cancel out. When you do FOIL, the middle terms cancel out. Let's look at FOIL and see if the middle terms cancel out. You do first, 7 times 2 is 14. Outer, 7 times negative root A is negative 7 root A. And then inner, 2 times positive root A is positive 2 root A. And last, a negative times a positive is negative. Root A times root A is root A squared. So did the middle 2 terms cancel out? No. So it's not, they're not conjugates. Conjugates, the middle terms would cancel out. However, do the middle terms combine like terms?
Yeah.
Yeah, they sure do. So what's negative 7 root A's plus 2 root A's?
14 root 8.
-7 root
Negative
a's
14
plus
a.
2 root a's? -5 root a's.
Oh, we're not multiplying, just
We're
kidding.
not multiplying. Good kid. And then what's root a squared?
A.
Yeah, just minus a. Now, can we combine anything now?
No.
No, because that's a number, that's a root a term, that's an a term, so we're just done. If you wanted to, you could put a 1 in front of the a.
Does
So
it
it's-
need to be rewritten so that it goes in order?
Well, you know, since it's a root a, there's not a strong order to go here. I suppose you could do the first variable to the first, and then -5a to the 1/2, and then plus 14. I see no real value in that. I would be perfectly happy with just the first one.
Okay, so that was what was bothering me before, in the problem at the end. So when a is to the 1/2, it doesn't mean 5 is also to the 1/2.
Correct.
Right?
No.
So it's almost like there's little brackets around the a.
Correct, there are brackets on the a, because it's just a that's being square rooted.
Right.
Is 5 being square rooted?
No,
That's
but
just a 5.
it's tempting to want to like include it. with
It's
the-
tempting, but resist that temptation.
Okay.
Because
That was
it's
where I
5,
had the question.
is 5 being square rooted?
Not there, but it's harder to see when you go down a step.
Well, let's do it like this. You had a 5 root a, right?
Uh-huh.
Little dot there, that's multiplication. And then put big parentheses here and here, and really bracket it off and say, over here, I got a 5. And over here, I got a root a. And now I have a 5 times an a that's being raised to the 1/2 power.
Right.
Is that 1/2 on the 5?
No.
Couldn't be further away.
Yeah.
Yeah. Okay, well, great, folks. How about this next one? You know, at some point, I gotta leave you something to do for homework. I think you could do that one for homework. Quick question. Are you allowed to just square both of them?
No, it's
No.
foiling.
It's foil. It has to be foil. This is confusing, though, because if you had 3 root 5 squared, then you would simply square both terms. But that's only because it's 3 times root 5. Since this is addition, you have to do FOIL. So there's one for you to do for homework, 3 plus root 5 times 3 plus root 5. Let's keep going. You know? Ah, okay, great. I was hoping that we would get to this today. Ooh, oh, we got some real good questions coming up here, folks.
Yay.
Okay. Let's just take a breather here for a second. At the beginning of class, we talked about the idea of simplifying. Simplifying, for instance, a fraction. What does it mean to simplify a fraction? What is it?
Divide.
Oh, well, yeah, that division, but how do you simplify a fraction?
22.
Well, yeah, it become 1/2, and the numbers become smaller. Now, that's a rule in life. At a math party, if you didn't simplify the fractions, everybody would be mad at you. They'd ask you to leave the party, right? So it's a normal part of mathematical life that you always simplify fractions. You just do. And then likewise, root 12. You can simplify root 12 because that can be rewritten as root 4 times 3, which is root 4 times root 3, which is 2 root 3. And so you simplify it to 2 root 3. And again, that would be a standard expectation of you at a math party, that you would always simplify it, the root 12 to 2 root 3, for the same reason you would simplify a fraction. Part of this is just sheer politeness, right? If you rolled up to a party and you said 144 288ths, nobody would like you. 'Cause- yeah, it'd be very, very rude, you know, it's contemptuous to say that that's the answer when you could just say the answer is 1/2, right? So there are certain rules of mathematics that we follow just because that's what it is. And if you didn't simplify it, it would be a party foul, right? Party foul. Okay, so we have a whole nother idea here called rationalizing the denominator, in which you probably just want to write this down up at the top. Yeah, because there's room up at the top. You are not allowed to leave a square root in the denominator. You are not allowed to leave a root in the denominator. Now, you might say, well, why is that? That seems like a strange rule. Why am I not allowed to leave a square root in the denominator? And I would like to at least give you an indication of why that would be so. So let's say, on your calculator, go ahead and do the square root of 2. What is the square root of 2?
1.4142.
1.41 what?
4142. You want the whole thing?
Yeah.
13. Oh, you got the 1. 3, 5, 6, 2.
Okay. But technically, folks, you all know it keeps going forever, right? Okay. So I want you to imagine 2 different division problems. Either root 2 divided by 2 or 2 divided by root 2. They might look almost identical. Like, who cares? You're just dividing. But in this particular problem, I'm taking this number and dividing it by 2. So if I do my, long division, 2 goes into 1.41421356. Dot, dot, dot. Which means this is a division problem I can do, and I just keep doing it as long as I want to do it to get more accuracy, right? So I go, 2 goes into 14 7 times, 14, 0, 1, doesn't go into 1, drop another 4, 7, 14, drop another 2, that's a 1, and so on and so forth. I would just keep dividing. But look at this problem. I'm saying to take 1.41421356 and divide it into 2. Well, I didn't finish writing this number down yet. How do I know how many times this goes into 2? I haven't even finished writing down the number. This is distinctly different. I mean, I could say that this goes into that once, for sure, and then I would write down 1.41421356. But see, unless I write that whole number down, and I bring all these zeros down, at some point I'm going to just cut it off and say, okay, I'm just going to go that many decimals. And then I keep doing the division problem. But since I just cut off all those decimals, if I keep dividing, I'm going to lose accuracy. So this is truly different. I don't even know what this number is. I'm not done writing it down, so I can't possibly divide it into that. And if you do, you'd lose accuracy. Whereas this one, as far as I want to keep going, I can keep getting more accuracy. This one, I necessarily lose accuracy. What is it?
She put it in her calculator, but she didn't have enough parentheses, and so it gave her an actual answer.
Okay. So at the very least, folks, I don't know if that really sold you on it.
I liked it too, but it wasn't right.
Okay. You're not allowed to leave a denominator in the root. That's what mathematicians have agreed. You are allowed to have a root in the numerator. So you might want to put a little picture here with it, okay? So you could have root 2 divided by 2, and that's okay. But if you have 2 divided by root 2, that's not okay. You're just not allowed to leave your answer like that. You're not allowed to leave your answer with a root in the denominator. Now we call it rationalize the denominator, this procedure that we're doing. It's called rationalizing the denominator. So rationalize, perhaps you all know the word rationalize in everyday life. What does it mean to rationalize something?
To make it have an answer, even though it doesn't necessarily, like an excuse, basically.
Yeah, you're making up an excuse, right? Like earlier today, I was out on the mall on Gateway, and I ate a big piece of chocolate cake. But I was like, that's fine. I can go running later this afternoon. Everything's fine. So what am I doing? I'm rationalizing my behavior. What other examples of rationalizing your behavior do you have? Just from today. I'm sure we've all rationalized something even today, let alone over the course of our lives. We've all had to rationalize decisions. Like, well, I shouldn't have done it, but I did, and it's okay because, I got this benefit. Do you guys know what I'm talking about?
Yeah.
Rationalizing? Okay, yeah, the way we lie to ourselves, right? Well, rationalizing the denominator does not mean that. We're not talking about rationalize something like making an excuse. We're talking about making it rational. So remember, a rational number
The ratio.
is a rational number like 1/2 or 2/3 or 5/1 or anything that can be written as a fraction. An irrational number, there are really just 2 types of irrational numbers, and those are roots that can't be simplified and pi. Okay, roots that can't be simplified and pi. Those are 2 big examples of irrational numbers. So when we say rationalize the denominator, we mean make it a whole number. We mean take that denominator that is currently a root and make it not a root. So that's what the phrase rationalize the denominator means. It means, hey, you see that irrational number in the denominator? Make it rational. So we want to get rid of the root 6. Now, what's that? Okay,
Square
well,
the whole thing.
well, you're not allowed to just square the whole thing. Because if you square the whole thing, you change its value.
Right.
We want to do something that doesn't change its value. And we have already seen something that you're allowed to do that doesn't change its value. What can I do that doesn't change its value? Multiply it by 1. Right? If I multiply it by 1, did I change its value? No. But multiplying by 1 doesn't make much sense. So instead we multiply by 1 over 1.
The square
Because-
root of 6 over the square root of 6.
Yes, we're going to multiply by the square root of 6 over the square root of 6. We're allowed to because the square root of 6 over the square root of 6 is really just 1. So if I multiply by the square root of 6 over the square root of 6, first of all, I hope you're all convinced that root 6 over root 6 is 1. Do you believe it?
Yeah.
What's root 6 divided by root 6? I mean, on the one hand, 6 divided by 6 is 1, so root 6 divided by root 6 is root 1, but the square root of 1 is just 1. So for sure, root 6 over root 6 is just 1. And so we are allowed to just take a number and multiply it by 1 because it doesn't change its value. So we're going to multiply by root 6 over root 6, which gives us, on the top,
Root 6 over 6.
yeah, because root 6 times root 6 is root 36, which is just 6. And we've done it. That's it. That's the end of the method. We just rationalized the denominator. So there once was a denominator that was irrational, that's not allowed, and now we have an expression where the denominator is rational, and that is allowed. You'll notice now that there's a root in the numerator, but that's okay. See, mathematicians are okay with a root being in the numerator, but they're not okay with a root being in the denominator. Now I encourage all of you to type both of these into your calculator. See that they are the same. Type them both into your calculator and make sure you get the same answer. Because we don't practice witchcraft in here. This isn't just so many symbols that we're pushing around. We want to see that it's real. So let's see here. 7 divided by root 6 is 2.85. And then the next one, 7 times root 6 divided by 6 is 2.85. Okay, good. I got it. They're the same. Okay, so we basically just manipulated some symbols, right? We manipulated the expression so that it wouldn't have a square root in the denominator, and we call this process rationalizing the denominator. And that's what we're going to practice now for a while.
So for number 75, would it be 9 root 2 over 2?
For number 75, it would be 9 root 2 over 2.
Okay.
Yep. But now let's do this one first. Slightly tricky. Well, no, it's not really tricky. I take back that I said that. So what do we have here? We have negative. Now how do I take the square root of a fraction? Root the numerator, root the denominator. And root 81 does simplify. That's just 9. And root 28, does it simplify?
No.
Is there a square number that goes with 28? Yeah, 4 times 7. So that's really 4 times 7, which is root 4 times root 7, which is 2 root 7. So yes, this is 2 root 7. Okay, thus far what we have done is simplified as much as we can. We have now simplified. But now we have to follow the other party rule, which is to not leave a square root in the denominator. So what's the square root in the denominator that we're not allowed to keep? The root 7. So what am I going to multiply by on top and bottom?
Root 7.
Root 7 over 7.
Okay.
We're not going to multiply times 2 root 7 over 2 root 7 because that would be excessive. We would end up having to simplify that 2 right back out again. We're only going to multiply the irrational part, top and bottom. And so what do we end up with?
Negative 9 root 7.
Yeah, negative 9 root 7 over,
2 times 7.
yeah, you'll always just want to memorize that a root times itself is just the number. Root 7 times root 7 is just 7. So now we have 2 times 7, which is just 14. So our final answer is negative 9 root 7 all over 14. Yep. That's it. That's how you rationalize the denominator. Does it appear to take a few steps? Yeah, it takes a few steps. Especially because, see, we had to square root a fraction, so we square root top and bottom. We simplified as much as we could. Then we had to rationalize the denominator, and then we had to simplify that. So you know, it's a long chain of reasoning, which honestly is what you're supposed to be learning in a math class, is how to follow a long chain of reasoning. You know, that makes us better humans, better able to participate in the political debate, understanding what's happening in the world. You have to be able to have a long chain of reasoning. Okay, so these next two, 75 and 76, go ahead and do both of those.
Oh, you put it in, don't have a
Did you ever get one?
Oh, let me give you one.
I'm sorry, Anna. I should have asked before class started. Here you go. Does everyone have a packet? Okay. So Layla already said the answer for 75, but what did you end up with for number 75?
9 square root 2 over 2.
Yeah, 9 root 2 over 2. And the answer for 76?
4 root 11 over 11.
Yeah, 4 root 11 over 11. Because again, you multiply root 11, top and bottom, and you have 4 root 11 over root 11 times root 11 is just 11. Nothing very exciting happened, did it? I mean, okay, great. We learned a skill. We're doing it. It doesn't seem that exciting because we're just following a rule that we've been told we have to follow. So that was just a straightforward example of rationalizing the denominator. It becomes a little bit more sophisticated when the denominator is a binomial. Now the denominator is a binomial. Now, before you read all that stuff up at the top, just do you think that if we multiplied now top and bottom by root 6, would that work?
No,
Why not?
because you'll get 9 root 6 minus 6.
Yeah, because now you'd have 4 root 6 over 9 root 6 minus 6. Did the root go away? No, it just kind of shifted, didn't it? It moved to the other value. Well, what if I was like, fine, do it again. Multiply by root 6 and root 6 again. Is that going to get rid of the root 6?
Nope.
No, because now on top we'll have 4 times root 6, which is 24. And then on the bottom we'd have 9 times root 6, which is 54, minus 6 root 6. So things are getting worse. The root 6 hasn't disappeared, and my numbers are growing. So this method is definitely not working. And why is it not working? Because what's happening in the denominator? We're subtracting. We've got an addition problem down there in the bottom. So what we want to do is get rid of that root, but because it's an addition problem, we have to have a slightly more special method. And it says in order to rationalize a binomial denominator, you have to multiply the top and bottom by the conjugate. So remember, conjugates, an example of a conjugate would be like a plus root b and a minus root b. That would be conjugates with roots involved. It could be more or less than that. You could also have root a plus root b and root a minus root b. Right? It just has to be the same numbers, but one of them is plus and one of them is minus. So what conjugate are we going to multiply by? Since the denominator is currently 9 minus root 6, what will we multiply top and bottom?
9 plus.
9 plus root 6. Yeah. We'll just do this one problem. Because then I'll pass back your test from last week, or the week before. So we multiply by the conjugate. This is definitely one case where you want to have your difference of squares formula memorized. You want to have memorized the difference of squares for 9 minus 6 and 9 plus root 6 because it's a simple formula and gives you the answer. So remember, I'm going to put the formula here for you. A minus b and a plus b. The answer is simply a squared minus b squared. So if I apply the difference of squares formula to 9 minus root 6 and 9 plus root 6, what will my denominator be?
81 plus, oh, top. Yeah.
Yeah, applying the rule without simplifying anything, it would be 9 squared minus root 6 squared. Now obviously you probably could have done all that in your head, but I wanted you to see the formula. So 9 squared is 81, and root 6 squared is just 6. And that finishes our denominator to be just 75. For sure, we just rationalized the denominator. The denominator started out as irrational, and now our denominator is rational. We started out with a root in the denominator, now our denominator is just a whole number. That's what we mean by rationalize the denominator.
Did you say like root 6 is just 6?
Root 6 squared. What happens when you square a root, Hazen? Yeah. Okay, well that's just the denominator. Again, you want to have this part memorized. It's one reason we learned it earlier. And then for the top though, what are we doing? You just distribute. Yeah, you just distribute. So 4 times 9 is 36. And then what's 4 times root 6?
4 root 6.
Yeah, just 4 root 6. And that's it. We rationalize the denominator. Now again, I would encourage all of you to take out your calculators and verify. Right? Trust but verify. Isn't that the phrase? So if I do 9 minus root 6, I get that one. This answer originally was 0.61. And now if I go down here and do root 6 times 4 plus 36 plus 75. Hey, goody, I also get 0.61. So sure enough, both of the expressions are identical. They have the same value, I should say. They're obviously not identical, but they have the same value. And what we say is that we have rationalized the denominator. You rationalize the denominator.
So you wouldn't combine the 36 and 4.
Well, you tell me. Can you combine the 36 plus the 4? Here's another example of that, okay? Wait, who just said that? Was that? Okay, Anna. Can you do 36 plus 4x?
Oh.
No, because that's an x term and that's a number term. This is a root 6 term. The root 6 acts just like a variable, making it such that you can only combine like terms that are other root 6s. So had it been 36 root 6 plus 4 root 6, then Anna, yes. Then you could have said that's 40 root 6. But since they're not the same root, you can't. David, pass back test. Hold on here, brother. You're missing out on a couple minutes of class, Davey. I can't give you a refund.
Oh.
There's David.
Hey, did you put a pasta on your dog's
All right, Alex.
Really? Wait, who is this? Oh, I didn't see it.
Jeffrey. Maria.
Where was this actor?
Claudia. Oh, wait, is this part of your list too? That fell off. Uh-oh, where did that come from? Everyone check your test. One of your pages fell off the back page. You're missing number 20. Somebody check, was that you, Olivia? Everyone check your test right now. You're missing the last page.
Oh, I
Someone.
am.
Are you?
Yeah.
Yeah, you are. Layla. Oh, and Anna, this was your practice.
Oh my gosh.
some of the graphy thing.
Yeah.
Thank you, folks. There's still 1, 2, 3, 4, 5, 4 pieces of candy left up here in case anybody wants some.